yeah, let's start from the example of clones. So from the second page, yeah, I was telling you that there are two ways of presenting clones, and the first one is to give you generators, for instance, and then I wanted to give you some examples on clones over two-element set. So Peter, please. So yeah, these are clones that during the talk then are going to play a role. So that's why I'm giving them a name. So first, if I consider the clone generated by the empty set, this is, as you would expect, the clone of all projection on a Boolean set. Then I denote by I2 the clone generated by the usual mit operation on a Boolean set and the usual minority operation on a Boolean set. And one can see from post lattice that this is exactly the clone of all idempotent operations over 0, 1. Then also we allow constants. So the clone generated by the constant operation 0 is also a clone. And also this will play an important role, as you will see. So the other way of presenting a clone of operations is actually to consider all those functions that preserve a certain set of operations. So let me just recall you what does it mean for an operation to preserve a relation. If I have an n-array operation, I say that this preserves a k-array relation R if whenever I take tuples that here in the picture are these rectangles, and then I apply f component-wise. So please, Peter, maybe I just raise. Then again, what you obtain as a new tuple is a tuple that is still in your relation R. And next again. So yes, in this case, I also say that R is invariant under this operation F. And then I say that F is a polymorphism of a relational structure A if it preserves all the relation of that structure. And as usual, I will denote by poly the set of all polymorphism of A. And I will call this the polymorphism clone of A because it is indeed a clone in the previous sense. And on the other side, I can consider a set of operations F and consider all those relations that are invariant under this set of relations. And you probably are seeing where I want to end up. I want to present the well-known Galois connection between clones and relational structures. And so, yeah, next slide. First, I want to define what does it mean for a structure to PP define another structure. So I'm given a structure on some signature and a PP formula, and a formula on the same signature with n free variables from x1 to xn. Then I say that the relation defined by this formula phi is exactly the set of tuples that witness the satisfiability of this formula in the structure A. And then in particular, if phi is primitive positive, I say that this relation is PP definable in A. And then we have two nice results that give us the Galois connection. And the first one tells us that a relation R is PP definable in A if and only if R is in inf pole of A. And on the other side, if S is a set of operations on some finite domain, then pole of inf of F is exactly the clone generated by this set of operations. And because of this nice Galois connection, it's well known, but let me repeat it, we gain for free that the set of all clones over a fixed finite set of n elements forms a lattice where the order is given by the usual set inclusion. And so I will denote this lattice by Ln, meaning the cardinality of the set we are considering. And this is a complete description of L2. Probably this lattice is better known as post lattice. But also from the Paul-Galois connection, we can see this result, please, as taking all Boolean structures and ordering them up to PP definability, because exactly PP definability of relational structures translates to clone inclusion of the corresponding polymorphism clones. Okay, so one can ask, we have a complete description of L2. What about clones on a 3-element set? Here, there is already a way worse situation. It's a well-known result of Janov and Mushnik that already from a 3-element set on, there exists a continuum of clones. So in particular, there are a continuum of clones on a 3-element set. So subsequent research then focused on doing the best. So they try to at least describe part of this lattice. So they started from, so we have a complete description of maximal and minimal clones on a 3-element set. But later on, we have that for every, so if we pick all maximal clones and we consider the downsets for each of these maximal clones, we have that for every such clone, with one exception, that is the clone of all linear functions, there are continuum many subclones contained. So Peter, you can a bit do the animation, but yeah, we have 2 to the omega many clones for each of those, with one exception. But later on, next slide, Dimitri Zhuk recently showed that actually continuum is not such a big problem, because despite continuity, he managed to give a complete description of one of these downsets. Indeed, he took the clone that contains all self-dual operations on a 3-element set and provided a complete description. And in the next slide, you can see a picture of this beautiful lattice. And as you can see, actually, in the 2 potatoes where it's written 2 to the omega, it's the only, they are the only 2 areas where we have continuum many clones, and all the rest is rather tame. And yeah, well described by Dimo. So continuum is not a problem. However, having a complete description of L3 seems to be behind hope anyway. So we need something stronger. We need a new order. And in general, when working with clones, we might have noticed that even though 2 clones are distinct as clones, they are somehow not so different. So for instance, we are looking here now for equivalence relation where clones that share some particular properties that then I'm going to define more specifically are in the same class. So what can be these properties? In this talk, I'm going to, so one such property could be, for instance, clones that satisfy the same identities. And in this talk, I'm going to consider particular identities. So for me, a minor identity is an identity of this form where I have equality, and in both sides of the equality, there exists exactly one operation symbol appearing. And then minor condition is a finite set of such identities. And let me just give you some examples of minor identities. Well, commutativity is a minor identity, while associativity is not, because I have nested use of symbols. But also the Maltsev identity, the Maltsev condition itself is not a minor identity, a minor condition, but there is a common trick in the CSP community to make it a minor condition by simply plugging, instead of y, m of y. And in this way, we get the quasi version. And if you know what a Maltsev condition is, you can always go to the quasi version of this Maltsev condition, linear Maltsev condition, sorry, and you will obtain a minor condition. Okay. And let me just briefly say what I mean by that a clone satisfies a minor condition. In general, it means that I can assign to every equality that appears in a minor condition sigma and concrete operation in the set in this case in the clone, such that every quality that appears in the symbols, it's actually an equality between operations in the clone. Okay, so let me give an operation, a motivation of why I'm actually considering such order. So I want to define what a minor is, and please, Peter, you can go at least 2 steps. Yeah. So exactly, whenever I have an operation F and the map sigma, I can actually define a new array operation as follows, as it's written in the formula there. And every such F sigma obtained in this way, I will call it a minor of F. And then I'm going to define a new notion of minor preserving map. Actually, this is a new notion. It comes from the 2015. And as you can see here, I require that such a map preserves arities, and then it behaves well with composition between projections. So it is a generalization of clone homomorphism, because I no longer require that projections are mapped to projections, but I rather require that I only preserve composition with projections. And as you might know, there is a semantic characterization of clone homomorphism between clones, which says that there exists a clone homomorphism from A to B if and only if B is in the expansion of HSP of A. And recently, in the Wonderland of Reflections, please, just next step, yeah, we have a very similar characterization for the notion of minor preserving maps. So, and this is done by introducing a new operator called exactly reflection that is coarser than H and S together. So I get this new characterization, but what's the problem? That exactly a reflection of an operation clone needs not to be a clone. It might be, so it's because it needs not to contain projections or to be closed under composition. What we get is a minion, a so-called minion, but not a clone. So we don't get for free that the PP constructability poset. No, it was okay. It's a lattice, but we actually still don't know, and we will have to gain that. So the other motivation here, I will be brief. I already stole too much time, probably. It comes from CSP. So yeah, let's skip what the CSP is, because those who know already know, I guess. But let me just say that I can define the same poset via PP constructability. So in order to define PP constructability, I would say that P is a PP power of A if it's isomorphic to a structure that has as a domain a power of A and whose relations are all PP definable from A. And then I say that A PP constructs P if P is homomorphically equivalent to a PP power of A. So again, why this poset is nice to be considered? Because it actually provides log space reduction, so it preserves the complexity of the CSPs, meaning that, sorry? Okay, yeah. So this is the right poset somehow to consider for CSPs. Next slide, please. Again, so here I collected together the 3 different characterizations of the same actually poset. And so let me just say that actually motivated by the CSP and, as I said, by classifying clones, we actually obtain great results recently. For instance, please, such a great achievement is the solution of the CSP dichotomy theorem. And first of all, from the CSP community, this is a positive solution to a long-standing conjecture that was opened since '98. And in order to get such a solution actually, new tools to understand finite algebras have been developed. So, for instance, absorption or the Bulatov theory or strong subalgebras, all these new notions helped us to understand finite algebras better. And so, yeah, we can state the CSP theorem in 3 different ways, depending on which one, which is like from which perspective you want to see the borderline between P and NP for finite CSPs. Please, next slide. So yeah, here I saw that Peter already showed you that it is equivalent to say that A does not PP construct the complete graph on 3 elements, and this is equivalent to say that, for instance, the polymorphism clone of A does not satisfy any non-trivial minor condition, and so on. So this was actually just the introduction, and now we are ready to define properly the poset, that is the object of study. So we saw that the existence of a minor preserving map gives rise to a quasi-order. So it actually makes sense to use less or equal as a symbol. And as usually we do, then from a quasi-order, I will define the corresponding equivalent relation, and I will say that 2 clones are minor equivalent if if there exists a minor preserving map in both sides. And then I will denote by overline C the M class of a F clone over finite set C. And then what I'm actually considering in this talk are 2 kinds of posets. In one, I consider all the M classes of clones over some finite set. So I don't put any bound on the domain. And then instead, if by Pn, I denote the clone over an element set. And we can prove that the PP constructability poset looks like this. So we have a top element, which is the M class of the clone generated by any constant operation, actually. So for instance, say a 0. And then we have a unique coatom, which is the clone, so the minor equivalent class of the clone of all idempotent operation on a 2-element set. And one can show that this is actually the same as considering all idempotent operation over any finite set. And on the same way, on the bottom, we have the clone of operations of 2-element set, and these are the same as projection over bigger sets. So both Pφ and Pn, actually for any n greater or equal than 2, the shape looks like this. And then because of the previous slide, so yeah, here I have, when I think about the PP constructability poset, you can also see it via PP constructability. So either you think about clones with the existence of minor preserving maps or finite relational structure with up to PP constructability. This is exactly the same thing. And because of the previous slides, one can show, also next step, that we exactly have only one reason of NP hardness, and this lies in the bottom of our poset. So every other relational structures that does not lie in the bottom has a tractable CSP, a CSP that is in P. Okay, so let's see how powerful are actually these minor preserving maps. I already showed you the post-lattice. This is clones over a 2-element set up to inclusion. What about clones on 2-element set up to the existence of minor preserving map? This is what we get. A lattice that is still countable, countably infinite, because of the presence of infinite descending chain. You can see it on the right, but it's, I would say, much more simple, and it has only 3 atoms. And I will come back to this again. But there is another lattice that I showed you during the introduction of this talk. Next slide, please. Exactly. So the lattice of clones of self-dual operation on a 3-element set. This was completely described by Dimitri Shuk. I told you that this is a continuum lattice, so a lattice with continuum many elements. And actually what we get up to minor preserving maps is the following lattice. So not only much more clean and simple, but this time, more remarkably, this is a countably infinite lattice. So we have reduced continuum to countable. as I said, there might be no hope maybe with the current tools that we have to describe clones on a 3-element set up to inclusion, but up to minor equivalence, this seems to be, there is hope to do this. And this will still give us, for the reason that I explained before, a good understanding of clones on a 3-element set. Okay, let's go ahead. So now I'm going to present you some general results about pfin. So I told you that we don't know whether pfin is a lattice or not because we don't have a Galois connection, but we know that it's a semi-lattice. So if I have two finite relational structures, A and B, I can define, and for every operation on pole A and G on pole B, I can define a new operation H on the Cartesian product, which exactly does what you would expect. So it's defined component-wise, and then I can define, so please forward, Peter. I can define gamma of A times B as follows. It will be inf of such operations that I previously defined. And then I define a new structure, A times B, which is defined exactly, yeah. The domain is the Cartesian product and the relations are given as previously. And this is exactly the meet operation in our lattice. In our poset. We don't know if it's a lattice. So let's go ahead. I'm sorry if I'm running. I feel I already stole some time. So the next natural question is to following the storyline of the story of clone theory is to ask what are the maximal elements and the minimal elements, right? So what are the atoms of pfin? Are there atoms in pfin? We can show that actually pfin has no atoms if we do not bound the domain. And how do we do this? I will just show you a sketch of the proof. What I want to show you is that if you give me a finite structure which is different from the bottom element, I can show you that there exists another finite relational structure that lies slightly, so strictly below this structure A, but which is still does not collapse with the bottom element. And in order to do this, well, from the fact that A it's different from the bottom, and from a result of Barto and Kojic, it follows that A satisfies some cyclic identity, which is an identity that looks like this, for some P greater than the domain of A. And then what I do is I take as B, so, and yeah, I will denote this by sigma P. I take as B exactly the meet between this structure A and CP. And by CP, I denote the relational structure whose graph, if you draw it, is a directed cycle of length P. And yeah, I will be quick here. This is exactly the witness that we were looking for because it's strictly below A and is still non-trivial because it satisfies some other cyclic identity, which I denote by sigma Q. It just take any Q that is bigger than, that is prime and bigger than the product between P and A, the cardinality of A, okay? So we have no atoms in the whole pfin, but what if we actually bound the domain? Well, recently there is a new notion from Barto, Brady, Bulatov, Kojic, and Zhuk, which is called minimal Taylor clones. They try to introduce this notion in order to unify exactly the two proofs of Bulatov and Zhuk in a unique theory. And we know, please, that every atom in pfin, so if overlying C is an atom in pfin, then actually C is a minimal Taylor on the same set from 0 to n-1. What about the converse implication? So is it true that actually also the other way around holds? Well, for n equals 2, I already showed you that from Schaeffer's theorem, we have 4 minimal Taylor clones, which are the clone generated by join, the clone generated by meet, by majority, which I denote by D3, and by minority, M. And the atoms over P2, as I showed you before, are just 3 because join and meet are collapse. And so this actually holds. But if we already look at the 3-element case, we can, I will show you in the next slide that actually this is false. And yeah, so actually here I have this emotional statement that says that actually atoms, the notion of atom in on over Pn is actually a better notion than minimal Taylor algebras itself. And together with Zeb Brady and Libor Barto and Dimajuk, we have a full description of the atoms on P3. So, and this is how the situation looks like. So let me just explain you the picture briefly. Every big square that you, a big rectangle that you see represents the minor equivalence class. And inside these big rectangles, you can see algebras. So here I use the Bulatov notation. So blue edges for majority, red edges for semi-lattice, and yellow edges for minority or affine. And yeah, so you can see that actually not every minor equivalence class of minimal Taylor algebras is an atom. Just pick one of these rectangles that lie on a second or third layer. Okay, so I'm almost to the end, just another bit of patience. Next slide. So now I don't know the time anymore. I'm just going till the end, but please stop me if I already annoyed you. So we talked about the minimal elements. The next natural question is, what about the maximal elements? And I already told you that we only have a unique coatom, so it actually makes sense. So the non-trivial thing to do is to look at the submaximal elements. And on a 3-element set, so I don't have time to talk about bigger sets, but on a 3-element set, we know that we have exactly only 3 submaximal elements. And please, what are these submaximal elements? Is exactly the minor equivalent class of C2, where here by C2 I denote the polymorphism clone of the directed cycle of length 2, C3, same thing, but directed cycle of length 3. And then by B2 I denote the polymorphism clone of such a relational structure that I draw you. This is an important relational structure. If you know what the blocker is, this is exactly the blocker relation for the Maltsev identity. Okay. And next slide. I already told you that together with Dimajuk and Manuel Bodirsky, we classified all clones of self-dual operations up to minor equivalence, which means that we exactly describe the full subposet that lies below C3. And what we still need to do is to describe what lies below C2 and B2. And the next slide, yes, again a bit. Because of a result of Andrei Bulatov in 2001, we actually know that there are only finitely many clones with the Maltsev operation on a 3-element set. This means that, next step, what we have below C2 is actually very mild, in the sense that we actually we will have only finitely many elements. And it's below B2 that something weird can happen, that we, for instance, can have potentially 2 to the omega many elements. And yeah, I mean, actually in the last slide, in general, if we want to know the cardinality of P-fin, so no bound on the cardinality of the structures, we still have only to look what lies below B2, because of a result of Erhard Eichinger, Meyer, and Mackenzie, we know that there are only countably many clones over an n-element set containing a Maltsev operation. And I told you that B2 is the blocker for Maltsev. So everything that, so we can continue many clones only below B2. And last 2 steps. So in the next talk, actually in 2 weeks, again at PALS, Dima is going to talk about clones defined by binary relations. So clones that are of the form pol of some relations, but all the relations are at most binary. And yeah, so in 2 weeks. And then just one other thing, together with Stefano Fioravanti and Bernardo Rossi, we are actually trying to classify all Maltsev clones on a 3-element set up to minor equivalence. So in the previous picture, this will be the yellow area, which is tame, but still, if we want to find the full description, we have also to do this. And yeah, this actually was all. And this is the same picture that I showed you before about minimal Taylor algebras, but in Prague and with Libor Barto. Thank you very much.